Good afternoon, drone pilots. I see this is midterm week. So the good news is in my class, you've already done most of the hard work. The rest of it is flying and fun. You've done the hardware, you've done the firmware, you've done the software. So now it's flying and having fun. As far as the build goes, what's left is telemetry, which I'll discuss today, and the Raspberry Pi, which I'll briefly discuss today. And from then on, it's get in the cage, do your maiden flight, come out to the arc, and do your waypoint flights, and graduate. And then you can have that drone and fly whenever you want, wherever you want, as per the regulations that you learned in this class. So the Mavlink topic in telemetry topic is today's topic. So what is Mavlink? Mavlink is a very lightweight messaging protocol for communicating with drones and between onboard drone components. It lives a step above TCP/IP in the network stack. Before we get into the technical details of Mavlink, let's discuss where it fits in the drone ecosystem. So you're all aware of Linux. It's one of the three major operating systems. There is a foundation to contribute. There's a nonprofit, I believe it's nonprofit foundation that hires developers to contribute to the maintenance and improvement of Linux, called the Linux Foundation. It's funded by large tech companies like Google, Amazon, probably Microsoft. I don't know the details. Under the Linux Foundation, there are many other foundations. For example, the Drone Code Foundation. So that's a foundation for drone coding, and that's funded by many of the drone companies. And under that, there are several projects. One is PX4 Autopilot, which is a fork of ArduPilot or vice versa. They're very similar in one, I don't know which one is a fork of the other, but the PX4 has an MIT license and ArduPilot has the GNU license, which we discussed previously. Pixhawk is a series of hardware for flight controllers. So they're the industry standard, and they're more expensive and bigger, and they're less bleeding edge in terms of new features. So we're not using them for this class, but for mature industry drone applications, Pixhawk is the de facto industry standard for hardware, flight controller hardware. And then there's Mavlink, which is the communications protocol between drones, which we're discussing today. And then Mav SDK is a partner of that. And then there's Q Ground Control, which is a ground control station that's open source, just like Mission Planner. So all these are open source. Mission Planner and Q Ground Control are both ground control stations. Q Ground Control is available also on Linux, Mac, and Android and iOS. And I don't use it in this class because it's it is less familiar to me personally, and I believe it has slightly less functionalities for all the parameters and mission, but it's more or less equivalent. So Mavlink is the topic of today's discussion. So Mavlink is the language that drones use to communicate with each other and with ground control stations. So you've actually been using Mavlink to communicate already. Something is wrong. Apologies for technical difficulties. We may have to pause and fix this. So while I'm working on this, are there any questions so far about the class? Okay. Well, there's another engineering principle is have redundancy. So I believe my connector is not working. Let's see if it'll work now. Okay, let's cross our fingers. I switched to VGA. So in fact, that's the theme of today's lecture. Somebody asked me, Professor Burke, why do you have so many radios talking to your drone? Well, because we want to have a backup. So let's hope that stays stable, and I'll replace the other connector. And we don't need the super high resolution HDMI. VGA is fine for today's discussion. Okay, so Mavlink is the language that Mission Planner has been using to talk to your drone on the bench. All the work that you've done for me and for yourself and for your drone this quarter, whenever you connect Mavlink with a USB cable to the flight controller, whenever you connect Mission Planner with a USB cable to the flight controller, the language they're using to communicate is Mavlink. So they're sending a heartbeat, they're sending altitude, attitude, they're sending commands, and so on. So like everything, it's very well documented and it's open source. So I'd like to go in a little bit more detail about what Mavlink offers you, just the highlights. And then you can read the documentation if you want a specific function. So the first thing is the Mavlink packets are between 8 and 263 bytes, so they're very short. And they contain a header and then a payload. The header has the start, the payload length, the packet sequence 1, 2, 3, so you can count and make sure you're not missing any. The system ID and component ID of the sender, which right now is only 255. So they're thinking of upgrading that because that means you can only have 255 enumerated drones in a Mavlink system. So for Mavlink 3, that's one of the key parameters that they're going to upgrade to allow you to have a larger address space. So message ID then is the most important one. That tells you what kind of message is coming. And then the actual payload, it depends on the message. And then there's a checksum. So there's 255 message IDs. I'm going to go over the most important ones in the next few slides, the most important classes of them. So this first important class of message IDs are system messages, the most important of that being heartbeat. It's exactly what it sounds. It comes once a second and it tells you that you have a connection. So if you're listening and you don't hear a heartbeat after a few seconds, that means you've probably lost your connection to your drone. And in fact, Mission Planner will say that. It'll say no heartbeat after 10 seconds if you have voice enabled. So it's exactly what it sounds. And then there's some system information in there also. If we have time, we'll delve deeper into that today. The next set of commands, which you've all been using, is setting various parameters and getting various parameters. So you can pick a parameter, any parameter you want, and set it over Mavlink. Or you can request any parameter you want. What is the value of that parameter over Mavlink? Or you can request all of them. Well, that's a very important set of commands, is setting and getting parameters. GPS, location and orientation are very important messages. So there's a GPS raw, there's a GPS integer. So it's the lat, lon, altitude, relative altitude, basically your GPS location. And not just that, the status, how many satellites the GPS is tracking, what the signal to noise is, the H-stop, which we discussed. All the GPS information you possibly want is contained in these messages. Also, the orientation of the drone. So the roll, pitch, and yaw, which is determined from the inertial measurement unit accelerometer, the compass, and any other sensors you may have. So all that information is available via Mavlink. Radio control. That's another very interesting one. So you can actually send radio signals over Mavlink, which we have not been doing so far, but you can say, I want channel 1, let's say it's a throttle, I want it to be 50%. So it'll set the throttle to 50%. So that can be used in place of your radio control, or we'll see today, we can fuse them together. So anytime you have a Mavlink connection from any source, you can take full control of that drone. Control commands are another common set. There's short and long. And those are commands like take off and land. And there's low level and high level. And then there's acknowledge, because the drone has to say, yes, I've gotten your command, I acknowledge it. Otherwise, you say take off, you don't know whether it's going to do it and whether it's done it. You have to query it. So long and short are low level and high level, and I have a slide on each. Long are high level commands like take off, land, fly to this waypoint, disarm your motors immediately, etc. So for example, Mav command takeoff, that means take off and hover at a specific altitude. Okay, so that's a high level command. And then the short ones are more low level commands like set the servo output or set the mode to be guided, stabilized, etc. So there's a set mode command. And these all probably have getters and setters, so you can read it out also. So the long command can have up to 7 parameters. The short command can have up to 4 parameters. They have 2 slightly different message IDs. One's high level, one's low level. They both respond with an acknowledge. So the complete set of messages is on the Mavlink website. I'm going to take this opportunity to make sure that it's recording. Let's end the show. Okay. Okay. Well, I'll check it in a minute. Okay. And let's get my external mouse working here. So there's 255 commands. The full documentation is about, shall we say, hundreds of pages. So my external mouse isn't working. I have to do the trackpad. So there's system status. We can look at heartbeat to start. So heartbeat is not just a heartbeat. It's got all these fields in it. The mode, etc. System status that comes has all these fields in it. What kind of sensors you have, the battery voltage, the current, etc. So you can see I'm scrolling, and the right-hand scroll bar isn't moving very far. So there's lots and lots of messages. Pretty much anything you'd want to do, you can do. And I think there's a miscellaneous one. A student asked me before, is there a way to override it? So I think there is a miscellaneous one if you want. Okay, now let me see why Zoom is not recording. Does anybody know? Otherwise, I'll have lost this and I can't post it. Okay. Well, what? I did. I did log in. So let's quit everything. No, it's still going. But it's not visible. Okay, well, let's cross our fingers and continue.
It looks like perhaps it's not registered.
Register.
It says sign in.
Well, I did sign in earlier. We try one more thing. Let me just disconnect that temporarily. I think this is a Zoom bug, which I've seen before. Bless you. So I'm going to assume it's a bug.
Maybe through Task Manager, you can click on that, and maybe you can end whatever the Zoom.
Yes.
No, and then start.
I could restart it. That probably is the intelligent thing to do. All right. Let's try to restart it. So those are all the commands. and you can look at them in the privacy of your own home. Now, I think we can just do the slideshow here. Okay. Do you need to know the command's syntax? Well, of course, with ChatGPT, it can do everything for you. So the answer is no. But pre-ChatGPT, the answer is no, because they have libraries in various programming languages that are available to you. So you don't need to know the detailed syntax and write code to put the packet together and send it. Or when you get a packet, you don't have to write code to parse it. All that code is pre-written in various libraries and in all the languages, C, C++, Python, C#, the whole list. So some of them are more mature than others, and the most mature one is Python. So that's what we're using in this class, but you do you. And any of those languages have libraries that will parse the messages and then create the messages. So Python is what we'll use in this class. And again, to graduate from this class, you have to have it build a drone and have it execute an autonomous mission, take off waypoints, land. But if you want to continue, you can write code. In Python, I'll show you how to write some Python code or how to use ChatGPT to write Python code for you and run it on your drone. Okay, yeah. So I have a demo script that I had ChatGPT write for you, and I tested it and it works. So if you run that script, and next lecture is going to be autonomy and AI. So this lecture is just telemetry. Just so you know, there is a script under the advanced topics in the website, which is how to tell your drone to go into land mode. Okay. And if you get your Raspberry Pi working, let's look at that script. If you get Raspberry Pi working, then you can run that script and it will go into land mode. And that's what I call hello world. In land mode is, I figure, about as safe as I can make it do, because I don't want to make it fly to Timbuktu. So this is the script, and this is the tutorial that explains how to get that script on your Raspberry Pi, run it on your Raspberry Pi, and then the Raspberry Pi tells the drone, go into land mode, and the drone goes into land mode and lands. So we'll do more on that next lecture when we get into AI and autonomy. But for now, we're just wanted to talk about how do we talk to the drone. The telemetry is how do we get the information back and forth. So Mavlink is the language. And then within Python, there are packages that can send and receive and parse Mavlink packets. But how do we actually make the connection? So that's called telemetry. And so far, you've been using a USB cable and you've been sending Mavlink packets back and forth. But we want more. We want to fly the drone and not have a cable. Now, another way is to use an optical fiber. So one of my students that took this class in the spring now is doing a senior design project, and their team is using an optical fiber instead of a cable. And it's very, very thin and lightweight. And that can go 10 kilometers because the fiber is pretty lightweight. But you can't have a USB cable that goes 10 kilometers. It's going to be too heavy. So we want something with radio waves to do drone telemetry. So there are a lot of options, as you can imagine, because there's a lot of radio technology available to your generation at very low cost. So we're going to go over some of them in this class. I can't do them all in one lecture, but I have picked the best ones for you. So if you go to the telemetry page of ArduPilot, it'll talk you through all the different options, and it's got short range and long range options for hardware. So you could have cell phone, you could have a Wi-Fi, you could have Bluetooth, you could have Starlink, you could have Iridium, you could have your own custom modem, anything you want, as long as you can send bits between the drone and the ground control station and use Mavlink as the message language, you can control the drone. So anything is possible. So the short range list is shown here on the Mavlink, on the ArduPilot page. And it's actually, yeah, Wi-Fi is actually very short range. As we discussed, Wi-Fi is about 100 meters. So that's way less than 10 kilometers. So here are a lot of the short range options. Typically SIC radio, which is a custom 900 megahertz modem just for drones, was used, but it's bigger and it's more expensive, and it's just for drones. Some of these are becoming obsolete. Bluetooth has been around a long time. You can also use Bluetooth. That's also short range. So I picked this one because I'm the professor and I'm in charge, and you have to do what I say. So I picked this one for you, and you can decide in the reviews whether you like it or not. But or you can tell me in person. And if you do have an alternative, we can put it in place. But I'm going to explain this one today and give a demo. So it's ESP32. It sets up a Wi-Fi hotspot in the sky. There's a video that explains it. And that's your last build milestone before you can go fly your autonomous missions. And I'm going to show you how to do that in a minute, but there's also a video that walks you through that. The other option for telemetry that you have opportunity to use in my class, which I highly recommend you do, it's going to give you a little bit more headache, but I'm going to try to convince you in today's lecture that it's worth it, is to use a long range telemetry. Now here's a list of all the long range ones. So satellite, 4G, cell phone. Eventually everything's going to be on cell phones, everything's on the internet. That seems to me the direction of the future. That's my prediction, but not today. And probably there will always be local radios for drones anyways. I don't foresee a situation where cell phone connected drones are the only protocol used to connect to the drones. My prediction is that there will always be a radio backup. Now, I could be wrong. We'll see. But at this moment, cell phone telemetry is really not mature to the point where it's easy. And so we're going to do what is easy and available to you now. And if somebody wants, I can walk you through it on the cell phone. It's possible, but there's no off-the-shelf system that's really in large use. There's a couple small companies, sort of mom and pop garage shop companies, and they sell solutions. But because the FAA is not allowing long-range flights yet, it's really not exploded as a market. Okay, so Crossfire we discussed. And this one you already have on your drone. So I'm going to propose and encourage you to use a radio that you've already put on there. And all you have to do is change the firmware. You're gonna moan when I say that because you've done so much firmware change. So you can moan, Professor Berg, more firmware. But what you get is no hardware, and you get long-range telemetry to your drone, which goes as long as the ELRS, which is tens of kilometers. And it's no hardware. So I'll walk you through that also in today's lecture, and we'll do a demo. So that's the two topics for today's lecture: is the ESP32 Wi-Fi demo, the ELRS demo, and then also I have at the very end Raspberry Pi demo, assuming things work. So there's also a video on
Good evening,
the ELRS. So I forgot which one we're doing first. No, we're doing the ESP32 first. So the first topic is the ESP32. So we have two telemetry hardware options we're going to discuss in the next hour: the ESP32 and the ELRS. So ESP32 is a microcontroller, and it has onboard Wi-Fi, and there's a firmware, of course, like everything else, that you can flash onto the ESP32 to make it a Wi-Fi hotspot in the sky. Then you can log onto that hotspot, and that's connected to your flight controller. And once you're logged onto that hotspot, Mission Planner or Q-Ground Control can control your drone over Wi-Fi. So that's ESP32. Beautiful, right? It is. So let's talk more about the details. First of all, what the heck is ESP32? Raise your hand if you've worked with ESP32s. Raise your hand if you've worked with STM. All of you raise your hand, because the flight controller is STM, okay? The brain of your drone is an STM32. So you have to say yes to that. So STM is a much bigger ecosystem and company based on the ARM architecture. It has the dominant global market share. And we discussed it when we discussed flight controllers. And I really wish I had recorded that lecture, but the notes are there. And there's thousands and thousands of variants of STM microcontrollers. There's 64-bit, 32-bit, fast, slow, high power, low power, you name it. And in the typical cell phone, there'd be 4 or 5, because one might be used just to run the display. You don't need anything special to just put pixels out onto a display. And one might be used for the really hardcore processing to run the operating system. That needs a powerful one. So STM is a very well-known microcontroller brand that is available. However, there's no integrated wireless. So that's a disadvantage. So if you want a wireless connectivity with a microcontroller-based system, if you use STM, you have to have a separate wireless chipset. So that's a disadvantage of STM. Now, ESP32 is an alternative microcontroller ecosystem. And it's based on either Extenza, which was a proprietary operating system, or architecture unique to that company, Espressive, but now they've moved to RISC, which is an open source architecture. It's a competitor to ARM, but it's free. ARM, there's a license fee. RISC, to my knowledge, is free. And RISC was invented at Stanford, and it's starting to take off again, I understand, for high-end processors. So there's but the nice thing about ESP32 is that it has integrated Wi-Fi and Bluetooth. So on the semiconductor, there's a Wi-Fi and Bluetooth transceiver. All you need is to put a little antenna on it, and you're good to go. You have Wi-Fi. The bad news is it's power hungry, so it's not useful for really low power applications. Now, as a drone pilot in my class and in general for other applications, well, let me ask you, half you raise your hand. What did you use the ESP32s for? Like, what were your use cases? Other than just hello world. Did you use it in class or out of class? Oh, I'm trying to have dialogue here. Half you raise your hand. I don't bite. It's just, or you just heard about it. Raise your hand if you've actually used an ESP32. 1, 2, 3. What'd you use it for? Rover. What about you? And what did it do? Control it?
And it wirelessly communicates with the rover.
So wireless connectivity, and then it controlled the rover. And it controlled the motors? So basically a drone. Basically, you built a drone flight controller with ESP32, but it wasn't flying, it was just roving. And you controlled it with Wi-Fi, right? That's what you did? Okay, so good for you. And there is actually a way to do that with drones. You can make ESP32 into a flight controller if you so desire. And some people do that. You don't get the barometer. So, but I think there might even be ArduPilot that runs on ESP32 because it's quite powerful. But you don't get the sensor, so it's more general purpose. Anyways, so they have a Wi-Fi. So as far as we're concerned, in this class and in general, there's a very practical advantage of using the ESP32 ecosystem, which is it's a Wi-Fi hotspot. And it's a Wi-Fi connectivity. It sounds like a small thing, but let me explain to you what it means in practice if you're doing projects. Number one, it creates its own Wi-Fi hotspot. Number two, it hosts its own website. So you create a hotspot, you have a website on board the microcontroller. Number three, on that website, you can change the parameters of whatever your project is. You don't have to use a USB cable. You don't have to download some proprietary firmware flasher. You can actually upgrade the firmware over the website. So you don't need anything. You don't need a laptop. You don't need Windows, Mac, doesn't matter. It's a website. You log into it. You configure everything through the website. You even flash firmware through the website. You can even upload files. It's got its own file system. So that's the advantage for us. And you're going to see why that's advantageous in today's lecture. But that's the general advantage of ESP32. So Espressive is the name. There's a whole variety of microcontrollers that they offer. We're going to pick this one, ESP32. Let me go back one and say, prior to ESP32, they had a family called ESP8266, which was relatively low computational power. But this, now they've raised the bar on computational power, and they're actually more powerful than most of the STM microcontrollers in terms of processing power. Not all of them, because there's a variety. So this is the one we're going to use. It's a 32-bit RISC processor with 160 megahertz, 400K ROM, 400K SRAM. The flash is contained in this board, so I think we have internally or externally a few megabytes of flash, and then onboard Wi-Fi, onboard Bluetooth, and all the things that any other microcontroller has. 22 GPIOs, 2 UARTs, 2 SPIs, 1 I2C, 1 I2S, 4 PWM out channels, we talked about that, and then 6 ADC channels. So everything but the kitchen sink, like most modern microcontrollers, with a really beefy processor, plenty of memory, and onboard Wi-Fi. So what else could you ask for? You tell me. And it's tiny and it's cheap, $5 to $10. So that's what we're going to be using for our telemetry. There's a picture. This is the antenna. Never power up a radio without the antenna connected. You might fry the radio. This is a very fragile connector. You have to put it straight on and pull it straight off. If you come in at an angle, you'll bend the pins and then you've bricked it. Don't ask me to fix that. That's really, I think I would just throw away and give you a new ESP32. So there's an external antenna. The radiation pattern is in the direction of the wire that's on top. So here's how you make it. You go to the kit, you go to the 195 cabinet, you look for DuPont drawer, you get the DuPont wires, you solder them up, you plug it into the UART, and you're done. This is where, so that's it. That's your last milestone. Then you've finished all the milestones you need for doing the autonomous mission. Like I said, the rest of it is fun. So that's pretty easy. I put my antenna on the arm facing down so that the radiation pattern is down, because the drone's in the air. I don't want to send Wi-Fi up to outer space. I want to send Wi-Fi down to the ground. However, if you fly way out and land way out on the other side of the arc on the ground, you might lose connectivity because it's facing the ground, it's on the ground. And there's a picture of the ESP32 in there. And there's the telemetry. There's the telemetry. This is the wiring, but I've already figured out the color scheme for you, so you can ignore that if you so desire. And that's all you do. So like I said, you have really worked hard this quarter. I pushed you hard early. We were very responsive and kept up with basically a sprint. And now you're at the point where you can start having some fun. So let's do that. And I'm not going to use the camera, but I'm going to connect to the drone wireless. I do need a battery. I will turn the radio on. I don't think I even need a radio. You don't have to move, it's okay. So this is the drone. I took the propellers off. It's powered on. That's all we're gonna do. I can just put it, here, say what? Go, you hold the drone for me, okay? So I show you. I'm not, nothing up my sleeves, just holding it on the floor there or something, okay? Just put it on the ground by your, not by me. Go away, 6 foot social distance. Yeah, just put it on the ground so we can see we're connecting wirelessly. So now I'm going to connect to the drone hotspot. However, I'm going to have to disconnect from the internet the way that this is set up. So I'm going to have to stop Zoom. So bye-bye Zoom. And I'm going to then instead record locally. Xing. Xing has my drone. I don't have it. He's got it over there. And it's just sitting there on the ground. The props are off, but it's powered up. And I can talk to it on my radio. You can see here I'm talking to it. It doesn't want to arm. So it's connected to my radio, but that's not what I want. I want to connect it to Mission Planner. So all I have to do is find the hotspot that the ESP32 makes. It's called Drone Bridge, and log in. And now, wait a minute, wait. Something is missing. Something very important is missing. Well, no, I'm sorry, I was wrong. That's about the other one. Okay, so let's log in. So get rid of ECI MobileNet. We're going to go to Drone Bridge. So that's a hotspot. I don't get internet connectivity, so Windows complains, but I am connected to the drone. It creates a local area network. So Windows takes a while because it's waiting to see if there's internet connectivity. And when it times out, it'll let me continue my lecture. Did anybody get the Wi-Fi Analyzer app on their phone in response to me? One did. Can you please try it? Thank you. I'll query you later. Just turn it on. Okay. Now, first of all, it's an ESP32, right? So it's got Wi-Fi. It creates its own website. There's the website. That's the website of the ESP32 microcontroller. And it's flashed with the firmware, which only takes a few minutes. And you can go in and change the parameters. So use these parameters. If you want details, watch the video. But you can see it's version number 2.1.0. Okay. So that's the website. So I'm already connected to the website, but I want to connect to the drone.
Mode change to stabilize.
There we go. It's connected. Just like you've been doing all quarter on the bench. Shing, is that how you say it? Can you wiggle it? Wiggle the drone. There you go. We're connected. So that's how you can connect your drone in the air. Thank you. Put it down. Okay. I think I'll leave it at that. Your range is going to be about 100 meters. So when the athletic field is about 200 meters across. So when you get about halfway across the athletic field, you're going to lose connection. So be advised. Now, just for fun, there's a Mavlink inspector on here, which you can also do with USB, that shows you in real time all the Mavlink packets that you're getting. So it's a little small, but like it shows you the GPS at 0. Let's do the attitude. It shows me the roll. It's minus 0.02 degrees. So can you move it again? Slowly, and let's see the roll angle change. So the roll angle is changing. That blue highlighted number is the roll angle. So these Mavlink packets are coming at different rates. Thank you. You can put it down. Most of them are a few hertz. You can adjust that in the parameters, but you can get maybe 1,000 or so packets a second. So you can get a lot of information. But yeah, so that's the Mavlink packets that are coming down. Okay. Shing, you're not done. I still need you, okay? There's more to go. Yeah, so what do you see on the Wi-Fi? You see the ExpressLRS, right?
Yeah.
Okay. What else do you see? We'll find out. But he sees ExpressLRS. You see in the back? ExpressLRS? Yeah. So you can get it within the room. So if anybody wants, you can log onto my drone now and control it. Yeah, it's ExpressLRS is the name of the password. Try. See if you can arm it. Make it beep. I'll do that as a hacking exercise, okay? When you set up your own, you might want to change the password. And please don't change my parameters because I got it all tuned up. So ExpressLRS passes Mavlink over the radio you already have. This was not available in last year's class. It only became available in December of 2024. And as I mentioned, ExpressLRS is an open source project, so I'm not saying you get what you pay for. It's actually pretty high quality, but the developers continue to add functionality. And you're welcome to also. It's open source. I was thinking of having Senior Design do this last year, but that's a little bit too much work. Anyways, this is a picture. So let's discuss it. That's the goal, is to have the drone connected to the mission planner over the ExpressLRS. So how are we going to do that? Well, what you have already is the drone is connected to the radio. And that's done. LoRa is the underlying protocol. And then on top of that is Crossfire. Crossfire is a proprietary reverse engineered protocol. Like I said, there's a lot of radio control protocols. There's Crossfire, there's DSM, and ExpressLRS is, from what I understand, reverse engineered the Crossfire protocol, which was invented by another company called Team Black Sheep. And now they're using that with open source hardware and firmware. So you're using the Crossfire protocol to communicate with your drone, which is fine. But that doesn't give you telemetry. That only gives you radio control. We want telemetry. So because ExpressLRS is open source, we can use any protocol we want. And so we're going to use Mavlink as a protocol to control the drone. And all you have to do is change a configuration setting. It's that simple. Because of course, there's some details, but once you change those configuration settings, now the drone and the radio are talking over Mavlink protocol. LoRa is still the underlying physical protocol, but Mavlink is the language they're talking. So like I said, Mavlink has RC controls as one of its possible messages. But we have 255 possible messages. So now we can get full access to the drone brain. We have Mavlink access to the radio, and the radio is connected to the microcontroller, the flight controller. So now we have full access, and it's two-way. So that's the first step, is to change that protocol and language to Mavlink for the control. And the second step is to forward from the radio to your computer all the other non-radio control packets, and vice versa. So that's what ExpressLRS enables you to do. Now, let me explain to you the hardware that you actually have already to do that, okay? And you have way more hardware than you possibly need. You have so many radios. So let's start with the receiver. You're well familiar with the receiver. It costs a few dollars. It weighs a few grams. And on board, there's a LoRa chip and a LoRa antenna. The LoRa chip creates the LoRa radio signals, okay? And the antenna sends them back and forth. But on the back of it, there's a microcontroller that controls the LoRa radio. The LoRa radio is dumb. It just sends radio waves and receives radio waves. So the microcontroller is needed to control what the radios are sending and receiving and to parse them. That microcontroller happens to be an ESP32. So ESP32 has built-in Wi-Fi. So they put a little antenna on here. So your receiver has a built-in Wi-Fi. Now, so far we have not used it because we're doing it a different way. Well, have we? No. I think we did. Yeah, we did when we flashed the firmware, right? So if the receiver is brand new out of the box, that's how we flash the upgraded firmware, is over the ESP32 Wi-Fi on the receiver. But then when we're done, we leave it alone. We don't use it. So we only use it to change. Now, if you lose your binding phrase or you forget it, you need to change the binding phrase of the receiver and transmitter, then you can do it over Wi-Fi for the receiver. Okay, so that's the receiver, but that's not what we want. We wanted the transmitter. So here's what I found, this really nice, useful website, OscarLang.com, is a picture of the inside of your radio, Master Pocket. And you have an antenna which is LoRa antenna. Inside there's a LoRa chip because it's sending and receiving LoRa. And then this is an ExpressLRS transit module. And then there's an ESP32 chip controlling it. And you flashed the firmware on it. That's one of your 5 nightmare videos, the 5 radio videos. One of them is to flash the firmware onto that of ExpressLRS and upgrade it to the most recent ExpressLRS so that both the ExpressLRS transmitter and receiver are on the same firmware version. And then there's a little Wi-Fi antenna on here. So inside of your transmitter radio is a Wi-Fi radio, which you have not yet used. Now we're going to use it. So you have to flash some firmware to enable that Wi-Fi. And then your radio, if I go back here, your radio will use the internal Wi-Fi as a hotspot. And then you can log into that hotspot just like I did here with Mission Planner. So that's all we're doing. And the rest of it is details. Now, it's time for a vote. Do you want the details first, which is about 5-10 minutes, or do you want the demo first? I vote for the demo. Do you want the demo first? Okay. Shing, you stand by. I'm going to need you in a moment. Don't touch it yet. Don't touch it. Pretend like it's in the air. Okay, so in the absence of objection, we'll do the demo. No, did anybody log into the other one yet? What happened? But then try Mission Planner. Okay, so this one is called ExpressLRS TX Backpack, and that has a serial number. The drone bridge has no serial number, so you're all going to have the same SSID. Please change it. But this one, luckily, each one has a different serial number. So this is the radio inside of my Radio Master Pocket. So here we go. 1, 2, 3, connect. And I think the password is ELRS. There we go. And I'm not going to log into that website. I've never needed to, but Mission Planner should work. Okay, so it seems to be working. So that's the ELRS. That's another way you can connect with Mission Planner. Now, what do you notice about the downloading of the parameters? It's slow. And the reason is LoRa is a low bit rate long range protocol. Wi-Fi is a high bit rate short range protocol. So that's a direct demonstration of the Shannon information capacity theorem and the free antenna transmission formula. Namely, Shannon information capacity theorem says the bit rate available depends on the signal to noise. So if you have a low signal to noise, which we have for long range radios, then you have a low bit rate. If you have a high signal to noise, which we have for short range radio, you have a high bit rate. So now you will never forget that theorem until the day you die if you take my class and use ELRS for telemetry. So we have to wait because of Shannon. But the good news is that can connect up to 10 kilometers away. So I invite you to try this at the Arc. Try this one. Fly all the way to the other side of the Arc. You should have totally stable Mission Planner signal. No problem. As long as you're patient enough. Now, it also means that if you're flying racing, this is not a really good way to do racing. The latency is significant. And so if you really want responsive stick and rudder control, you wouldn't want to use this protocol. You'd want to use Crossfire and if you're a drone racer. And we're going to see it again in a minute. Shing's going to pick it up and move it, but we have to wait. So the good news is there's no hardware to change. You have all the hardware already. Any questions while we wait? Is anybody coming to the 8 a.m. ABET thing? Because if 138 of you come, I have to buy 138 cups of coffee. And they're not all going to fit in one robot. But they want a couple students just to ask them how they like the class. Oh, good, we're done. Okay, now Shing, you're on. Wiggle it slowly. See how slow it is? Hold it up so the class can see. It's super laggy. Okay, just wiggle it right 90 degrees. And do a quick wiggle, just a quick 90 degree, and don't go back. Yeah, go like that just to demonstrate. See how it takes a while, and then go back up. So there's some significant lag there. So that's the bad news. Okay, so thank you. You can put it down. I'm going to have one more job for you in a minute, which is Raspberry Pi. So that's the demo. Now let's go back to the theory. Nobody wants to try? Come on. There must be one hacker in the crowd. Okay. Shing, can you hard power cycle it? So I'm disconnected here. Hard power cycle it. And whoever wants to can fire up their laptop and can log into my drone with either of those Wi-Fi. Just unplug it and plug it back in. Either of those Wi-Fis and try to control it. Okay. And if you give it a command like arm, it'll give you the do. That means I'm not ready to arm. Okay. Because I need to explain the parameters, and then I also want to do the last demo, which is the Raspberry Pi. Okay. So you have to change all sorts of parameters in all your different radios. The radio inside of the radio master pocket, the parameters have to be changed. The radio receiver on the drone, the parameters have to be changed. The RGPilot settings and Mission Planner, the parameters have to be changed. So there's a long and a short PDF tutorial walking through changing those parameters. I'm going to show you the short version. But if you want a full step-by-step tutorial, it's PDF and YouTube that walks you through every single step and holds your hand, read the long one. Because we only have 20 minutes, I'm going to do the short one. So this is the short one. Both systems have to have RGPilot settings like that. If you want to stay on the Crossfire protocol, which is what you already have, these are the RGPilot settings for the radio. And I updated the settings, the parameter file on Canvas due to a problem with compass calibration. So there was a memory issue because microcontrollers only have so much memory. So one of the parameters needed to be adjusted because we're using a lot of the memory. So use this updated parameter file for Mission Planner. But I didn't change this. This is just telling the UART that the radio is connected to what protocol to expect. So it's telling it to expect Crossfire. That's what we already had. So you've already done that. And on the transmitter, you're sending Crossfire. You've already done that. And on the radio receiver, it's receive Crossfire. You've already done that. Okay. But actually,
receiver still connected.
Can you reboot it again? I'm going to try the live demo of changing the parameter on the radio receiver. So if I go to that, if Shing reboots it, my transmitter is off, so you can't hack into that now because it's off. But the radio receiver will go into Wi-Fi mode, so I can log into it and change its parameters from Crossfire to Mavlink. So I'll show you that in a minute. All right, so to use Mavlink and ExpressLRS, here are the settings. In RGPilot, you have to tell the radio to use protocol 2, which is Mavlink. So you have to tell the flight controller to expect Mavlink packets from the radio receiver on the drone. It's not expecting Crossfire anymore. And everybody has to be speaking the same language. So that's the flight controller. And then on the transmitter, you have to change the internal radio, the ESP32 module, the ELRS module. So you have to make it Mavlink, and you have to turn the internal Wi-Fi on so that you get the Wi-Fi hotspot. So this is done in a tutorial, the long one, and this is a snapshot of the menu items that you have to adjust with the radio interface. Okay, so you change to Mavlink. So both of them are speaking Mavlink. They're speaking the same language. You have to turn on the Wi-Fi hotspot. And then the radio receiver also has to be expecting Mavlink. Now, is that is the green light flashing green yet? The on the bottom, I have my radio receiver.
Yes.
Is it flashing fast?
Yes.
Okay. So the radio receiver now is not talking to ExpressLRS, is not talking to the transmitter because the transmitter is off. So I can go into that one and tell it to speak a different language. This is how you do it. You go into that and you go to that website, which is 10.0.0.1. So it's not working. It's sometimes the ESP32s can be a little bit flaky. Okay, there it is. So that's the receiver. It says right here, happy model EP2 2.4 gigahertz RX receiver. So if I want, I can come down here and change the serial protocol to whatever I want. Now I've already changed it to Mavlink because I've already done that. So that's that one. So that's what you have to do there. Presenter view. Okay, you can put it down now. We don't need it yet. So this is showing what I just did there. And then we did the demo already. Okay, so that's the Mavlink demo. Now, this allows you to connect Mission Planner. But there's one more, and that's really useful out of the field, one or both of those, to connect to the drone wirelessly while it's in the air. In fact, you're going to need one of them to do the autonomous mission. Because to do the autonomous mission, you have to put it in auto mode. And we only have 3 modes on the radio. So to put it in auto mode, you're going to have to connect the computer to it. Then once you put it in auto mode, it'll fly the autonomous mission. So you will need one of those 2. Now, like I said, last year, a lot of students finished early. They wanted more material. So this year, we're adding the Raspberry Pi. So there's one last demo, which is Raspberry Pi. Now, I will talk more about internet-connected drones next couple lectures because that's the wave of the future, and also onboard computers with autonomy. So our flight controller, it turns out it's pretty dumb. There's no file system really. You can't upload any code to it. So it just does what it's told, but there's no way to do any real scripting on there. The most recent microcontrollers, the H7s, you can upload a Lua script, a short Lua script, and that'll run within ArduPilot. But it's pretty low amount of processing power. So there's a concept called companion computer or onboard computer, which is you put a computer on your drone. And then the computer can be whatever kind of computer you want. So that's what we're going to do. And because our drones are small and we have a limited budget, we're using Raspberry Pi 02W. W being the important word because it has wireless on board. And Raspberry Pi being a full Linux machine. Okay, so in the following lectures, we'll talk more about how to configure that. But I'll give you the short version. You all know what this is, right? That's the DuPont 0.1-inch header pattern. So all you have to do is solder 4 DuPont 0.1-inch headers to this. You've already done 50 for the flight controller, so you need 4. And you get 5 volts in ground to the Raspberry Pi, and then you get TX and RX for the Raspberry Pi. And you use a spare UART on your flight controller, and if you configure the software on the Raspberry Pi, now the Raspberry Pi can send Mavlink packets back and forth between the Raspberry Pi and the flight controller. So in principle, you can keep it that way, and the Raspberry Pi is now in charge of the drone. And that's what the Hello World script is. The Raspberry Pi sends a command to the drone saying land. That's what I just showed you. And I don't have it set up now, but I will in the next lecture. But it's a simple Python script. You run it on the Pi. It sends the command to the drone, tells it to land. So if you can have Python do that, you can use Python to do whatever you want. What I want to demo today, at least, is the connection to the flight controller through the Raspberry Pi. So there's a hotspot on here, which we create, which I'm going to log into. And then I've set up the Raspberry Pi to forward traffic back and forth with a program called Mavlink Router. So Mavlink Router is a software package that does exactly what it sounds like. It routes Mavlink packets from one destination to another destination. And I have it set up to route Mavlink packets from its Wi-Fi to its serial port. So let's do the demo of that. So I might need your services soon. Not yet. So the Raspberry Pi is on there and it's connected. So let's log into the Raspberry Pi. Where is that? Uh-oh. Shane, you're fired. Is it connected? Okay, don't touch it. Probably it's just too much Wi-Fi in here. Drone bridge. Yeah, no, I see it. Anyways, so that's 3 Wi-Fi now. The person that had the app, he unfortunately left. His loss. So if you pull up the Wi-Fi Analyzer app, you have ExpressLRS, which we did. You have Backpack, which we did. And now you have Raspberry Pi Hotspot, which I'm about to do. And you can see all those on your Wi-Fi Analyzer. So please let me, Wi-Fi people, please let me get it. There it is, Raspberry Pi Hotspot. And I forgot the password, but so you can't hack it unless you can guess my password. I don't think it's secure, probably. So none of this is encrypted, by the way. Mavlink, all this is unencrypted. So if you ever want to do something important, you're going to have to provide your own encryption. It's not built into all these protocols. Anyways, so there's the Pi hotspot, and now we have to wait for Windows to time out because it's not going to connect to the internet. No internet. So let's look at that in detail. It's a hotspot. There's the IP address of the internet, 10.42.0.1. So we can go to Mission Planner and connect to that. And I think you see where I'm going with this. Because if I can do it over TCP/IP, then I can connect to it from anywhere in the world. So I already have tried it before, 10.42.0.1. And I have it programmed to do port 5678 because that's easy for me to remember.
Mode change to stabilize.
Okay. Now, as soon as it finishes, Shing, I want you to get up and move it around. This one should be pretty fast too because it's Wi-Fi. So this is the Wi-Fi going to the Raspberry Pi, from the Raspberry Pi to the flight controller and back. And you can, yeah, wiggle it, please. So it's working.
Error compass variance.
Okay, thank you. That's enough. Now, don't leave yet. You're still not relieved of duty. So let's try now. Just to show you, it's a Raspberry Pi. I'm going to log into it. So the YouTube videos and the tutorials teach you how to flash to get Raspberry Pi going. By the way, how many of you have ever used the Raspberry Pi? Most of you. How many have used it without a keyboard and a monitor? A few of you. How many have used it exclusively without a keyboard and a monitor? None of you. So there's a way to do it, which is very easy. You flash the firmware or the operating system to the SD card, and when you flash it, you tell it the Wi-Fi SSID and password. And then it saves that when it flashes the operating system. And then you also have to tell it you want to enable login remotely. And then as soon as you turn the Raspberry Pi on with no keyboard and monitor, it connects to the Wi-Fi network. And if you're on the same Wi-Fi network, then you can log in you can get a terminal called SSH. So in my first video on internet connected drones, I walk you through that. And you don't have to ever have a keyboard or monitor ever connected to your Raspberry Pi. So you don't get any graphical user interface, but you don't need one. There is no monitor on your drone. It's in the air. So we got a few minutes left. I forgot what that address was. You remember? 10. What? Smart students. So there we go. Now I'm in the Raspberry Pi. Okay, so I can list the directory and I can make an example file. There's the example file text.txt. I can cat it to the terminal. There it is. So it's a full Linux computer. And you can download his scripts on there. You can install Python and do anything you want. It's just limited by the processing power. So that is the one. Then you'll log in, you'll get the script, run it, it'll go into LAN mode, and then that will allow you to do autonomy in the future. So that's internet connected drone. Okay, so that's telemetry. Happy flying.